All right, good morning, everybody. So we are starting out today's lecture, and in this part of the week, we are gradually transitioning towards the so-called small activities, beyond saturation, therapeutics. And the first lecture today will be given by Vladimir Korepin. He is going to give us the theoretical perspective on those topics, and in particular to health dynamics.
Well, good morning. Thank you, organizing committee, for inviting me. So please pay attention to the left side of this diagram. This is our DIS. Like this virtual photon come from the electron, and this is a proton, three constituent quark, valence quark. And then, as soon as the photon entered the hadron, the proton is split into a quark, a virtual quark and quark pair, and these virtual quarks interact with the valence quark, exchanging gluons. On the other hand, gluons interact between themselves. That's our subject of interest today: interaction of those gluons. This is BFKL actually. So eventually, so these gluons will be my chain, will be my spin chain. So I'll explain what spin chain, and next there will be some introduction. Spin chains are standard object of condensed matter, statistical mechanics, maybe quantum information, but I will introduce it. There will be some mathematics in the first lecture. 19th century mathematician discovered Lie algebra of the SU3, so it was used in high energy. But in the 20th century, they discovered quantum groups. Quantum groups kind of deformation of the group, and one of them is useful for us. It's called Yangian. So I will explain. Yangian quantum group has some applications. So let's move. So the introduction, as Alexei correctly pointed out, our main subject of interest is gluon structure function. Gluon structure function at small x. It's a power. And this power, I can get approximation if I consider two gluon exchange. It's called Pomeron approximation, Pomeron. Then this is the expression for the power if I take into account only exchange of two gluons. But by now, in this lecture, we want to take into account correction coming from more gluons. I don't know, 3, 4, 5, 7, maybe all of them. So, and then the idea of this study of multi-gluon exchange will be to study the information spread in this spin chain. So I'll explain spin chain, and information will be more on Friday. On Friday, I'll give another lecture. Okay, so what is spin chain? So first spin chain was discovered in 1929. 1929, at that time, it was part of solid-state physics, and by now it's statistical mechanics. So I have one-dimensional chain, which is more or less our gluons, but we'll return to gluons later. So this J is a number of the latest site of gluon, but now it's latest site. In each latest site, I have spin 1/2. Spin 1/2 represented by Pauli matrices, 3 of them. So SU2 representation, spin 1/2. This is interaction. Two nearest neighbors interact. I mean, it's called the isotropic interactions, evidently invariant under the SU2 rotation. I can rotate this. But there is more hidden symmetry, that Yangian symmetry. When the length of lattice is infinite, there's another hidden symmetry, this Yangian symmetry, which is useful for BFKL. Okay, so first of all, change notation. Mathematician doesn't like Pauli matrices. They like this basis, like AB, this is 0, 1. So this 2x2 matrix, I can take the basis instead of Pauli matrices. This matrices which has all zeros except of 1, 1, 1. And this 1 situated on the intersection of the eighth row and B column, so SAB. Basically, this is linear combination of Pauli matrices. This is the same Hamiltonian. I mean, how's my accent? How do I speak too fast? Is this more or less? Okay, ask questions. This is unusual subject, so don't hesitate. Yes?
That's sigma plus and sigma minus, right?
You know what? Not quite.
Okay.
I mean, so 0. Yeah, actually, I changed my plea. Yes. I changed, yes. But except of sigma matrices, I have a projectors, right? This is also S11. So it's not sigma matrix, it's square equal to itself. So some of them are sigma plus, sigma minus, some other projectors. Sigma plus, sigma minus, the two projectors, that's all. All right. So this is just a standard normal commutation relation SU2 algebra or 3 normal rotation, so nothing unusual. Now move. So now this Hamiltonian of my XXX spin chain is invariant at the SU2 rotation. So if I take all the local of these sigma pluses and sum up with respect to all lattice sites, so I get the global rotation. It commutes with the Hamiltonian, so general rotation. It's kind of clear of the way it was written. Nevertheless, there's another generator. So now we're extending. We want this SU2 will be subalgebra of our Youngian. So now we want to add to more generators. So this is the next generator. This actually Youngian is infinite dimensional algebra. So the next generator is Q1. So Planck constant, which is 1, don't worry about. Here, summation with respect to all pairs of the lattice sites. So any distance. And this is like my AD, those bases. So it's different, right? So commutation relation of the S0 is the same as U2. Q1 of, commute with S0 as vectors, but the commutation of two Q1s is somewhat non-trivial. This is just, first of all, I can take this and check that this is true. On the other hand, I can look, just let me finish the sentence, and I can look into Wikipedia. In Wikipedia, there is Youngian lecture, and then, or I can ask ChatGPT. Yes?
Q0 is 4 1s on each side?
Yes. Those is sigma plus, remember, sigma minus, then 1, 0, 0, and 0, 0, 1.
And is there an QAB? I don't know what this charge is, Q1AB?
Q1AB is so I take one of those in one lattice set and some other in other lattice set and sum up with respect to all the pairs of lattice sets. So it's like large double sum. Well, the reason it's not familiar because it's like Youngian. It's like it was not very much used. Yes.
Is there a reason why this looks like an angular momentum operator?
Yeah. There is later we shall. You know what? I was mathematician the previous life. So first we introduced this mathematically, and there is some interpretation. There's also Lucier introduced this the charge, but it's in better than yes. So what you said is the physical meaning of this. So I just prefer to proceed mathematically formally, but we'll come to physics. Anyway, there is some commutation relations. Well, they're also in Wikipedia. Just dial Youngian, it will come up. There is also all of this has to be self-consistent. So there is in algebra there's a mathematician, French mathematician, Serre, and this is Serre relation, meaning this Q1 Q0 satisfies this, and this actually guarantees that everything is self-consistent. So this is a nice algebra. This is not the end of this presentation. Nice presentation is on my website. So Vladimir Korepin, many web pages will come up. Somewhere in the middle of my work, there is a Denis Bernard, he's French, and he wrote nice introduction to Youngians. This is also you have the website, the file, PDF file, so you can click. It will come up. So the detailed explanation, physics and mathematics of Youngian. All right. So those Youngians. Let me do something else. So this commutes with the Hamiltonian vectors. This also commutes. But then I also can make powers of this. I can multiply Q0 by Q1 or consider some crazy polynomial. Those also will commute with Hamiltonian. So by this nonlinear function polynomial, I can construct infinite dimensional algebra because each polynomial. So that will be basis of Youngian as linear algebra. So Youngian. Anyway, so it has multiple applications to physics. Maybe the most essential to us is Nicholas Beiser. I guess he's from Switzerland. He wrote a paper. Actually, this is YouTube. So movies. You can watch movie. This is application of Youngian in supersymmetric Young mills. It's actually commute with this, and it's useful. But I will use this Youngian as application to BFKL, to our GIS. So you get some idea of Youngian. There are more quantum groups. There is much more young quantum groups, but what's essential for my lectures is this Youngian. So let's proceed. Okay. So Youngian, you get a hint of the Youngian. Now, this remember I have this Hamiltonian XXX Heisenberg Hamiltonian. So it was diagonalized by Hans Bethe. That's the same Bethe who was mentioned, famous Hans Bethe from nuclear physics. He also diagonalized Heisenberg in 1922, like 100 years ago. And the technique of diagonalization called Bethe ansatz, named after him. So I will explain this in the lecture, main ideas. So let me give some hints about this Bethe ansatz. So it's important for us because this Hamiltonian, similar Hamiltonian, will describe interaction of these gluons coming down, and we want to diagonalize them in order to calculate correction to delta to the power of x. So we have to suffer a little bit or learn new things. This is a school, right? So learn new things. So except of Young, there are many other conservation laws in this Hamiltonian. So let me write an example of other conservation law. This XXX Hamiltonian has infinite many conservation laws exactly solvable. So another one, summation with respect to the lattice side. I have one Pauli matrix, another Pauli matrix. Now these two in the neighboring lattice side, JJ plus 1, and here anti-symmetric tensor A, B, C. So and the sum through the whole lattice. So this thing comes to the Hamiltonian, so conservation law, and infinitely many. So it's a special model. It's not usual. It's not a generic. It's integral. In the sense of Newtonian dynamics, when you study Newtonian dynamics, you saw integral. It's integral. Okay. So many conservation laws. So this Hamiltonian, we can say that it describes spin waves. Spin waves will be waves of color when I return back to GIS. And remember that my spins are actually gluons, so this will be waves of color. So spin describes scattering of spin waves. The spin waves scatter on one another. Scattering is sometimes denoted by R. Well, at least in my lectures. Individual moment of spin waves conserved. I mean, if I have like 22 spin waves scattering each one dimension, right? So scattering through one another. After scattering, they will come up. The individual momentum of the waves can be transmuted, transposition, but the set individual moment conserved. Okay, so it's special. Many-body dynamics is reduced to two-body dynamics. So among other things, many-body scattering matrices is product of scattering matrices. This is very strong and very special. Doesn't happen in all the models, but it happens in these Bethe ansatz solvable models. So for consistency, this scattering matrix satisfies some cubic relation called Young-Baxter relation. And this is like famous, and Young is my Young. I work in the Young Institute for Theoretical Physics. And Baxter is a famous expert in statistical mechanics. He's from Australia. So this Young Baxter helped to diagonalize and machinery called Bethe ansatz. In the end of this lecture, there will be a couple of transparencies about technicalities about this Bethe ansatz. In principle, it's very similar to matrix product state formulation. This is like computer science application, numerical physics. And that's if you click, this is just in the matrix product state interpretation of this algebraic Bethe ansatz, which I will explain, which brings us the relate Bethe ansatz to modern life. This is a special case of tensor network, and in order to write this algebraic Bethe ansatz or matrix product state, I need an auxiliary dimension, bonded dimension. This is some new dimension which I introduced of matrices, which I mean can come out of nowhere, but they serve the purpose of I want to solve the model. So that's the reason I have to introduce extra dimensions.
I have a conceptual question. When we write down the sum of all lattice sides and we give the Pauli matrices two indices, what does we have the one index, like I guess the A, B, and so on, that's describing which Pauli matrix I look at. But the index J, what does
this is
describe?
X, Y, Z, 3, right?
Yeah.
And this is G go from minus infinity to plus infinity through integers. This is number of the lattice sides.
Yes.
Label of the lattice.
Yeah, but you only have like three Pauli matrices.
You know what?
Sigma
I have,
X.
listen.
Yeah.
You should think that this is many particles, and each has spin 1/2.
Yeah.
So this is Pauli matrix describing one gluon, and here another gluon. It has its own Pauli matrix, and that's the other one. So Pauli matrix, mathematicians say that we have like C2 raised in the power total length of the lattice, well, 1 to L, and then they are isomorphic, but they're in the different spaces because the particles are different.
Okay. Basically say that
Actually, they are isomorphic, but with different particles.
you could say that like J Pauli matrix acts on lattice site J,
Exactly true.
but it
That's
like,
exactly what I meant.
like commutes with anything that acts on lattice
Yes,
site
right,
J
right, right,
plus
right.
one.
J, this commute with this,
Yeah, okay.
with all of them, because they need
It's like
different
a
spaces.
tensor product.
Exactly. That's
Okay, okay. Thank you.
Thank you for the question.
Oh, I just wanted to ask the same question. Is
You want me to repeat the same answer?
It commutes with the nearest neighbor, it commutes with
Nearest
all.
neighbors and a lot of names. Different space, tensor product space, tensor product. So, I mean, one gluon and has this polymer, another has this, but they're different. They're different. You know, these little bit different notations of condensed matter, solid state, but you know, get used to this for my lectures. Okay, so now this is
Hi, you have.
what?
So I was under the impression that when you have infinite number of conserved charges,
Infinitely many, all.
infinite very conserved charges, in order for the Yang-Baxter equation to hold, they should form a Lie algebra. So
You know what? There is two things. This, the upper, the one, and many others. Well, I will explain construction of all conservation laws. So they commute with the Hamiltonian. This is like abelian algebra. But Yangian is something different. Yangian does not, Yangian's generators does not commute. They will form SU2 algebra and more, right? So we have two different things. So normal experts at the time know only about this conservation laws which form abelian algebra, meaning that they commute with Hamiltonian and with one another.
Yeah, yeah.
But Yangian is different. It is just some other conservation law. Additional, they appear only for the infinite. And they're not abelian. And their algebra is igual. Can I continue? Okay. So now this is technicalities already. So in order to solve the model diagonalization, I introduce extra dimension. So this L operator, L in the name, the first letter of the name of famous mathematician Peter Lux, who is invented all this. So it depends on lambda. Lambda is spectral parameter, basically it's rapidity. But it will, mathematicians call it spectral parameter. Sigma is our sigma. This is our quantum degrees of freedom, these quantum spins. But then I arrange them in matrix 2 by 2, and this is like a bond dimension or auxiliary dimension. I artificially introduce extra dimension, but I'm going to play a lot with this. For example, I will take this L. Well, N is the same like J. N is the same like J. So this number of the lattice set. I copied from the different papers, so they have different notation. N is J, number of lattice set. So I'm going to multiply operator in the different lattice set, but I multiply them. Oh, I should multiply matrices by the row by the column, and then I, construct some object which help me to diagonalize Hamiltonian. Anyway, this L operator, this is your tensor product. Somebody wanted the tensor product. So the commutation, so this entries of this operator does not commute between one another, sigma plus, sigma minus, sigma z. But nevertheless, I can assemble the commutation relation in this nice, this is Yang-Baxter, more or less. So this is two L operators. They in the same lattice set. So the same lattice set means that their sigma does not commute. I mean the SU2 algebra. On the other hand, the cross means that they have different bond dimensions. So this tensor product is 4-dimensional matrix, 4 by 4, and this is different order, right? And then this is the commutation relation of their entries can be represented like this, and our matrix is. I forgot now. Oh, no, it's identity 4 by 4 identity matrix, this permutation, and then lambda minus nu. So this is Yang-Baxter equation. So far, it's nothing new. I introduced some extra dimension and rewrote the commutation relation in some cute form. But this cute form will persist, meaning that I can later will multiply operators in the different lattice sets, keeping the same R matrix. So this will help me eventually to diagonalize Hamiltonian. Now you have to suffer through technicalities of Petanzas. Let's go suffer. All right. So that's a multiplication. So I have these operators, first lattice set, second lattice set, and multiply all of them as matrices 2 by 2. the row column in this auxiliary space. So I get some matrix, A, B, C, D. So A, B, C, D are operators, but A, B, C, D, each of them act on all lattice sites. They have all power matrices inside of them. So this is highly non-local operators. And later we shall discover physical meaning, like you like physical meaning. So this A and D contains Hamiltonian and all conservation laws. And D, well, I mean, eventually I will put this in the Taylor series in terms of lambda. This is some polynomial in lambda of the nth power. So I can put this in the Taylor series, and all the coefficients will be Hamiltonian and conservation laws, diagonal. B will be creation operator of the spin wave, in such a way that this is eigenvector of the Hamiltonian, and C is annihilation. So this construction makes sense. And then it persists the commutation edge. That's exactly the same commutation relation which I have here, but instead of L, I put T. I put T, this T. So our matrix is still simple. This is 4 by 4. It's no big deal. It's simple matrix. But this is really complicated beast by now because depending on all power matrices and eventually those diagonalized Hamiltonian. Nevertheless, I managed to fish out the commutation relation. So later this will help me to diagonalize Hamiltonian. That's it. All right. So this is my T, product of L operators. Trace meaning that I can add trace meaning A plus D. So A plus D called trace in the auxiliary dimension. After I took trace, my auxiliary dimension, bond dimension disappear. I trace it out. So I have A plus D. Those traces sometimes denoted by T small, but it depends on all the quantum operators, sigma plus, sigma minus, and then Hamiltonian and all conservation law can be extracted. Yes. See, it's tricky, right? The original L operator was matrix in two spaces. First of all, it was quantum operator, which is power matrix, which is 2 by 2, right? On the other hand, it also was matrix in this auxiliary bond dimension. So by now, I traced away bond dimension. So this T small is not a matrix in the bond dimension anymore, but it's still quantum operator in all lattice sites. It has all power matrices in each and every lattice site. It's a lot of sites. So it is kind of matrix. It acts in each and every lattice site in here, ABCG, in each and every lattice site, but bond dimension disappear. It's useful because now I can come back to physics. First of all, this was some kind of mathematical construction. What's the use? First of all, I can extract out of here my original Hamiltonian. This is 3 power matrices. I take logarithmic derivatives of this at some specific point, and I recover my Hamiltonian. And all I can take more derivatives at some other points. This will be my conservation laws. And this T of lambda commute with itself at different values of lambda. So this, mathematically, I took care of all of this conservation law, this abelian subalgebra. I collect them together. This is kind of generating functional of Hamiltonian and all conservation laws. Okay. Come back. Yes.
The previous slide, you pointed
Even previous. Here.
Yes, you pointed to something and you called it an annihilation matrix. Which one is it?
This is annihilation. It's operator. I won't call it matrix. Let's call it operator. And then this is creation operator. I mean, power matrices, I prefer to call quantum operators because the word matrix I keep for this auxiliary space, which appears sometimes as additional mathematical construction. Well, you want to solve the differential equation, you go through some tricks. This is my trick to diagonalize it. Well, it's not mine, I mean, young buck. Okay. So, yes.
Can we go back to two previous slides?
Oh.
Yeah. So what's the subscript 0 and 0 bar? What does this mean?
0 means that I wrote this as explicit matrix 2 by 2 in the auxiliary space. 0 is labeled, and 0 and 0 bar is our matrix actually in the X in the tensor product of two auxiliary spaces. So 0 bar. Okay, this is formal relation. But anyway, this is simple matrix 4 by 4. It never changes, so it's elementary stuff. This is very complicated because it has all the power matrices for each and every lattice set. But it's useful because we can diagonalize Hamiltonian.
A question. In the previous slide, when you
Previous?
I think one, yeah, previous one.
In here?
Oh, this is the next page, right?
Next page?
No, I mean the previous.
Yeah, this?
Slide 9.
Slide 9. Wait. Here.
Yeah, so on the top, when you define the sigma like product with SN, you mean like
I didn't understand the question. Can you repeat the question?
so in the first equation.
First equation.
that was-
This cross means I take sigma x as a quantum operator, then the product with this Sx, which is off diagonal matrix out of 1, 1 off diagonal in the auxiliary space.
Yeah.
And this is the y with the y operating the auxiliary space. So if I do this multiplication, I get this matrix.
Oh, sure. You
The result of this tensor multiplication.
add the x, y, z together.
Yes. The sigma x multiplied by Sx plus sigma y multiplied by Sy plus sigma z multiplied by z altogether gives this. So this is simple stuff. There's 3 terms here. So
Okay.
there's some formal notations.
Okay.
I try to move. Anyway, so you got an idea about this beta ansatz, so diagonalization of the spin chain. Okay, but so far, the quantum degrees of freedom was spin 1/2, right? Pauli matrices. This can be generalized to higher spins. Well, for example, spin 1. For spin 1, Hamiltonian, and that was J, so number of the lattice side go from minus infinite lattice. So X is this scalar product of the neighboring spins, but by now spins are matrices is 3 by 3 because it's spin 1, right? Not spin 1. So by now Hamiltonian looks a little bit different. So this is looks like original Heisenberg SS minus square. Square makes sense because for Pauli matrix, I square Pauli matrix, I get like some stupid constant, right? What?
Very sorry.
Previous?
Ninth slide again.
Ninth slide again. I like ninth slide.
Previous question. So when we have sigma Kronecker Sn, so this sigma means this.
Yeah, let me write it down because let me erase. So this thing, so what is this? S. So this means the following. I take sigma x as a quantum operator, multiply this by the matrix. Okay. First of all, first term 0, 0, sigma x versus, you know what, this should have been here. That's a typo, right? Just confuse everybody. Plus sigma y in this side in here minus I this plus sigma z and here have 1 minus 1 0 0. So these explicit matrices are in my auxiliary space, but one dimensional, and this is quantum operator. So I sum them up, all 3, and I got this more or less.
So, okay, so when we have a Kronecker product of, so.
This is tensor product. I mean, sigma x, n should be here. N should be here.
Yeah, okay, but my question is when we have this type of product between, because this matrix.
Quantum operator and auxiliary matrix.
Yeah, but it's written like a vector. It's sigma x.
Yeah, well, this is kind of scalar product of 2 vectors, right? X plus y plus z.
Okay, so it's like scalar product.
It's scalar product. You have a question? You always have questions.
Does it end like it's referring to the lattice?
Let's just say. I try to move out of 9. Okay. So far, you get a taste of spin 1/2. Now let's change the spin. Spin 1/2 is boring. Let's go to spin 1. So those are 3-dimensional matrices that represent as U2. This is X scalar product. Again, scalar product, right? N plus 1 was JJ plus 1. And this is Hamiltonian. X minus X square. For Pauli matrices, doesn't make sense to square because Pauli square is constant. In here, it's not trivial operator. And then specific construction because I want model to be solvable by beta ansatz. I want Young-Baxter beta ansatz. The solvability, that's the reason of the specific coefficients. It was Zamalogic. Okay. Later, it was generalized to high spin, integer and half integer. So this is actually some polynomial. So y is some numbers, like some numbers, integer numbers, and then x is this operator, but by now s is high dimensional because by now it's a spin maybe 7.5 or 175. So any integer or half integer spin in here. So for any higher spin, which is integer or half integer, I can construct solvable Hamiltonian. It will be solved by similar machinery. So this machinery, all of this tensor notation you suffered, but it's useful because you solve not one model, but many. Okay. So by now, so what I'm doing so far, I'm changing the dimension of the local representation of the SU2 algebra in here. In one, let's say, originally I have a power matrix divided. Then I had a three-dimensional matrix, spin 1, then high dimension. Eventually, I want other values of spin. I want like negative spin, I want fractional spin, like square root of 2. Then I have to make this infinite dimension. If I make a local space in let's just infinite dimensional, then I can construct SU2 representation with any real spin. Maybe square root of 135. Well, I will need my -1 actually. So by now we move to the other representation that you said. So we want to make local spills infinite dimensional. So meaning that we'll have a bunch of harmonic oscillators. So in each lattice set, I will have a harmonic oscillator, bosonic harmonic oscillator. So they commute in the different lattice sets. This kappa is the standard harmonic delta is the number. Lattice step of the lattice. The delta positive number step of the lattice from this point of view. So then I make some kind of, so kappa is coupling constant. This is square root of 1 plus the number of particles. So this is standard combination for harmonic oscillator. I put it in here. So my new L operator, linear, then psi number operator plus minus, and here I have creation annihilation with the square root. So these elements form the same representation of SU2. It's also a representation of SU2 in a different space. I can calculate the spin. Spin will come out to be negative number. It actually can be any number, any real number. So now I want to move it, and now this is actually BFKL. So don't be, it's useful. So now it's the end of the pedagogy. This is BFKL. So what I'm telling you that this is harmonic oscillator. Usually normal people denote this by A and A dagger. And then if I take this and this, I can commute, right? I know commutation relation. And then commutation relation, after my suffering of calculation, this is SU2 algebra. But the spin is not integer, it's not half integer, it's negative. And then this is our okay, so L operator. L operator has the same similar structure. So lambda, this SK is still matrices 2 by 2 in the auxiliary space. But this sigma, no. Sigma is an auxiliary space. Sigma is two-dimensional. This is still two-dimensional. But S is quantum spin in the set number J, and it's a creation operator, annihilation operator, and then this square root. So SU2 representation, and the spin is this. Spin is -2 K delta. And then later we shall choose kappa to be such that S is equal to -1. We want -1. This is BFK. All right. So this L operator and our matrix didn't change. Our matrix is the same 4 by 4. By the way, later we shall have other R matrix. I will comment on the other R matrix momentarily. We'll have to go to slide number 9 again. Okay, the Hamiltonian. So this is the L operator. L operator is some mathematical object, right? So how about Hamiltonian? So Hamiltonian looks somewhat difficult, somewhat complicated. So G, wait. Sorry. Operator. Yeah. G is local operator. I'll explain later. I'm going in the opposite direction. Yeah. Okay, so this J is a simple local operator, but still with square roots. I will explain it later. J and K is number of the lattice set, and psi is logarithmic derivative of a gamma function. This is BFKL Hamiltonian. All right. Okay, so maybe let's come to slide number 9, which I forgot. This is 14, so for me, not to forget. So, okay, so for people who like to suffer through mathematical notations, so in here, L operator both are in the same lattice site, so the same quantum space, but a different auxiliary space. I can multiply them differently. I can consider them as matrices in the same auxiliary space, but in the different quantum spaces. And then our matrix has to be infinite dimensional because our matrix will intertwine two infinite dimensional quantum spaces. And it will appear later, this other arithmetic. So there's two arithmetics, one simple arithmetic, so 4x4, and then later there will be another arithmetic, which will be infinite dimension. Well, it will be quantum operator make out of harmonic oscillates infinite dimension. We're not afraid of infinite dimension because we know harmonic oscillates. So anyway, let's move. 14. Okay. So this is a spin, negative spin, and this Hamiltonian regrettably complicated. Okay, so by now I can relate this to BFKL. So we suffered through spin chains, right, and got some education. So BFKL, mainly I will talk next time, but this is for people, Balitsky, Fadin, Kuraev, Lipatov. So they consider the photon momentum is very, very large, and they consider TMZ, the plane perpendicular to the plane. But they didn't consider momentum. So they consider Z as like a complex coordinate in the space perpendicular to this P. And then they try to sum up all of this contribution to delta from multi-gluon exchange. And they got Hamiltonian. So this is their BFKL Hamiltonian. Also interaction between the nearest Lewis side. So their Hamiltonian expressed in terms of P. So DDZ, the Z is a complex coordinate which describe my coordinates in the plane perpendicular to P. P is momentum of the virtual photon. So this is P, and this is Z, just coordinate by itself. So then BFKL after multiple summation, I will explain summation. That actually summation is very complicated. It's transcendental, it's mind damaging. But if you know Yangian, then it simplifies. And then there is some German guy who helped all of this simplifications of derivation. So this is Hamiltonian. And then, basically that's the same Hamiltonian which I just saw. So what I'm trying to say that this is just some operator, Z, the derivative with respect to Z, but I can rewrite this Hamiltonian, BFKL Hamiltonian by now in terms of SU2 algebra. That was done by Lipatov. And so the whole Hamiltonian depends on these combinations. This S minus is derivative with respect to Z for the case gluon. This is Z and S plus and minus. I can check. This is SU2 representation. This is SU2 representation. And then this is the other R matrix. Remember I told you there's two R matrices, right? One R matrix is normal 4x4, which I saw, and there's another infinite dimensional R matrix. So that's infinite dimensional R matrix, but it's exactly the same, which I saw in latest nonlinear Schrödinger in the one with spin minus 1/2. This is gamma function, and this is J. Remember I said that I will say J. So J satisfies this. J is a solution of this quadratic equation. This is quantum spin and latest set number J. This is quantum spin. This is the scalar product, like XX plus YY plus ZZ. And this is quadratic equation for this J. On the other hand, in this equation, within this equation, everything commutes between one another. So I can use like Viet formula to solve it. I know how to solve quadratic equation for commuting because everything commutes here. So I just write normal solution. So I take this J, put this in the Hamiltonian, which was logarithmic derivative of density matrix, put this in this R matrix. So meaning what? So this BFKL Hamiltonian, I can write as the logarithmic derivative of this R matrix, and the Hamiltonian is again logarithmic derivative of gamma function with this. So they match BFKL Hamiltonian match this XXX with spin minus 1. What? Number 9? Okay. There was Beatles had a song Revolution number 9, remember?
So why are we in imaginary space in the transverse dimension?
You know what? This is another, well, This is another auxiliary space. So you have to forget my one dimension, what is one dimension. So it's not the one. So by now I was saving this for the Friday lecture. So now I mean something completely different. So this is my electron, right? This is a virtual photon. And then it enters the proton here. I have a quark anti-quark pair, constituted quarks, but then I can draw a Feynman diagram. So I have a momentum usually Q, right? Which is very, very large, right? And then I want to concentrate my attention on the plane perpendicular to this. That's where TMZ lives, but I'm operating not exactly with TMZ because I'm not talking about the momentum. I'm considering this plane perpendicular to Q, and it's two-dimensional plane, so I can describe the point by two coordinates x and y, or I can write quantum number. I can write complex number. See, so Z is a complex number describing the position of a point on the plane perpendicular to Q, and it's unrelated to auxiliary space. Previous, that's different. Other, part of random access memory.
In that expression, the sum is over particles, right?
This is some of the gluons. Remember, we have in here this, virtual quarks, right? And then constituted quarks, and then gluon. So case number of gluon. So it is number of the lattice side, but lattice side for me is gluons. It's the same thing. By now it's glued together.
And we was trying to understand the periodic boundary condition in the sense of
Periodic boundary condition somehow PFK is suffers to this. It came out. It came out. I will give more precise references, and there is another lecture, and I will not be able to explain all the details. So general ideas plus references. So anyway, guys like me feel happy at this point because here Hamiltonian got interpretation, and this is spin -1 xxx. So let's see. Okay, we already been here. Well, that's a paper with a reference with all the details. Leipzig in Eastern Germany, right? The city, Eastern Germany. So Ronald Kirchner from Leipzig. So he published a paper. You click on this, and then here, Ronald Kirchner, he used this Youngian symmetry to derive BF-Kyle Hamiltonian. I skip a lot of the details, right? I explain what is Youngian, what is BF-Kyle. It's a kind of a fat paper. But if you want to suffer all the details in here, the file, PDF file belongs to organizing committee, you can click in here. So once again, this BF-Kyle Hamiltonian is this logarithmic derivative of gamma, logarithmic derivative of gamma, and this M, J sometimes denoted M is minus J. And I don't know, let's see. So that's a key reference. Okay, so by now, the physical part of my lecture is almost over. Right now, I want to return back to algebraic beta ansatz. Remember this ABCD, capital ABCD, in the beginning of the lecture. Yes, sir.
Can you go to the previous slide, please?
Previous slide.
So at the bottom, you have this formula of the Hamiltonian HJK.
Yeah.
And it's like the logarithmic derivative of the R matrix.
Of this.
Yeah, and if I remember correctly, previously for the spin 1/2 case, the Hamiltonian turned out to be the logarithmic derivative of the transfer matrix, right?
It is. You're right. This is local Hamiltonian. This is density of the Hamiltonian. So this is like one local term. In order to get the whole Hamiltonian, I have to put a k equal to j plus 1 and sum up with respect to all j. And then in order to get that full Hamiltonian, I have to differentiate the logarithm of the transfer matrix made out of this R. So thank you for your question. Okay, so this is the end of the main part of the lecture, but in the beginning, I remember I had these auxiliary spaces, algebraic beta ansatz, virtual, and I said that I give some hints and details on the derivation of diagonalization of the original spin 1/2 Hamiltonian. So now we have to suffer through some mathematics. It's like appendix. So we'll go through appendix. So back to spin 1/2, which is beginning of the lecture. It was 1929, 1932, 100 years ago. So I have this ABCD. ABCD was matrix elements of this transfer matrix, which you just mentioned. when I multiply all the L operators into auxiliary spaces matrices 2 by 2, then I get ABCD. Each of them was operator in each and every quantum space. So I need some vector. Like in Lie algebra, I want the representation, I need highest weight vector. So this is highest weight vector. Sometimes we do quantum field theory, so people call it vacuum, but it's not the ground state. It's not the ground state. It's some reference state. Vacuum, just a label. It's not the ground state. Some formal word. I should put quotation mark here. Well, since we talk about spin 1/2, I mean, local space is two-dimensional, spin up, spin down. So let's take ferromagnetic states where all spins looking up. So this is exact eigenvector of the Hamiltonian of Heisenberg Hamiltonian of 1929, spin 1/2. It also eigenvector. It's also eigenvector of this A operator and D operator, and this thing annihilated by C operator by annihilation. Remember, you were asked about C. You like C, so it's some use of that. Okay, and then for this ferromagnetic state for A, it's not. This is eigenvector of A, and eigenvalue of this lambda, my spectral parameter, which is rapidity plus I squared of -1 raised to the power n, and the total length of the lattice. So I change notation. N is total length of the lattice, number of the gluons. No? For D operator is similar, but eigenvalue is important. And then T transfer matrix, which David interested. A plus D, I can apply to this ferromagnetic state. I also get a number. Oh, I forget the brackets. I forget the lambda raised to the power. This is total number of lattice sites. Lambda plus I squared of -1. We had the brackets. I forgot the brackets. Well, this is just important starting point. So I can start my algebra, and then A, B, C, D. I know all the commutational relations, and a simple commutational relation because I use my simple matrix 4 by 4 in order to write them down. This matrix was like 1 plus permutation, no big deal. So simple commutational relation. So using those, I can construct eigenvectors of the Hamiltonian, of the original Heisenberg Hamiltonian spin 1/2. This, and this, it looks like this, the eigenvector. Now my ferromagnetic state, I applied several B operators, and remember B creation operator, lambdas. This is numbers in general, it's complex number. Unfortunately, it has to satisfy some equations. I hope I wrote them. This is algebra of the commutational relation of this A and B and C, which is RTT equal to TTR for in case when our matrix 4 by 4. So commutation relation between A and D is simple. For example, it's easy to move A through B. I just go through with some factor or they exchange. This is like a scattering process. Transmission or reflection. Here two moment exchange, and here they keep with some numerical factors. So I can use this in order to, so what I want to do, I want to calculate eigenvectors of this A plus D, the trace, because Hamiltonian is sitting in there. So first I apply this site to my B omega. So the result is somewhat horrible, but this first term looks like eigenvector, and here somebody killed. So one of the lambdas they replaced. One of the lambdas which are sitting inside of B replaced by the lambda of this. So I kind of don't like them because I want eigenvector. This looks like eigenvector. I want this like die, you know. So I put equation that lambda sub j equal to 0. Then my equation turn. This is the system of these equations. Lambda sub j equal to 0. This guarantees that B is eigenvector. And this is famous Bert equations. I mean, if you read any book on beta ansatz, by the way, there's like tens of books on beta ansatz. There's Wikipedia, ChatGPT. It's like very big field with many authors. But if you take any book on beta ansatz, first thing you will see beta equations. For normal people, this comes out of periodic boundary conditions, actually. And then they're usually in publications or books of beta ansatz. The whole center is this beta equation. So I, by the way, square root of -1. And this is the labels of the lambdas by now. It's not the latest sites. It's I have several lambdas, so I had to use the label. So beta ansatz somehow we'll be able to solve them sooner or later. And then I want the energy levels. Well, I suffered all of this mathematics. I want something back. So energy levels, eigenvalues of the Hamiltonian, they're given in terms of these mu's which satisfy that equation. So later in the next on Friday, 11 o'clock, we shall construct the ground state of BF Hamiltonian. and then use this to calculate central charge and move ahead for the calculation of the correction of the delta. We're still trying to calculate 1 divided by x and delta correction to Pomeroy. I think that's the end. Yeah. That's the end of my lecture for today, but there will be another one on Friday. And also I will come at 1 p.m. for discussion.
Thank you. All right, more questions? Vladimir?
Maybe.
Does this have some kind of connection to like the Ising model? Because that's
Isaac model is super great. It is solvable. I mean, the people who do better answers, they like think they're proud people, they're proud of themselves. So they say like Isaac model is free Fermions, this interactive Fermions, trivial. So I think it's solvable, but better answers people look down on Isaac. Because asymmetric scattering matrix, I think, doesn't depend on momentum. There is no bound states. And here, scattering matrix does depend on momentum, can be bound state in some, many models solvable by better answers. In one dimension, one space, one time dimension, many. Well, I can write the Hamiltonian. So I think it's solvable, but actually a little bit by different technique. Solvable, but not in this frame.
Was part of the purpose of this to start from these commutation rate relations between known spin half particles and bosons to get to this any spin, fractional spin commutation?
Oh, fractional spin. Well, the history was like this. So BFKL, okay, Z perpendicular to P, okay. The suffer, got this. And by the way, if you consider some kind of tree approximation for the scattering of the photon on these quarks, you will get, and then try to re-express this in terms of Z, right? And then it won't be analytical function in Z. So it looks disgusting. On the other hand, there is something which is called regionization, where I take a correction that one spin exchange the T channel, then non-analytical piece die. And then we got Z, which is analytical. But then they wrote this Hamiltonian, then they express this in terms of real algebra. And then actually the Hamiltonian, which they got, was spin 0. From our point of view, better answer, this is disgusting. 0 is like 0 dimension, I really don't like. Then there was paper by Karchemsky and Fadeev, they managed to map 0 to -1. Well, everything depends. Everything depends in Lie algebras. Everything depends on S plus 1, right? So S equal to 0. This thing is 0, but S equal to -1 also is 0. Yeah. So it works. So, but S equal to -1, then I got my mental concentration on spin equal to -1. And then I want to find, I work on better answers for many years. So I want to find some model which is solvable and has a spin -1. And then this lattice nonlinear string is a set of harmonic oscillators in the different lattices interacting in a very special form. The Hamiltonian is this crazy logarithmic derivative of psi, but all of this is because I want to match to BFKL and to use the technique, the multiple results of better answer to BFKL. That was the whole intrigue.
I skimmed this paper by Frank Wilczek on anions. So did he use this whole formula?
No, anions is different. It's different. I mean, they're great, but
He doesn't use these commutation relations.
You know what? This is like my language is arithmetics didn't depend on lambda. So this like braid group is a topological thing, but once again, it's different. Special quantity. Arithmetics for him. This 4x4 is non-trivial, anionic, especially if I want non-abelian anions, then necessarily it's symmetric, but it doesn't depend on lambda. So it's somewhat related, but still a little bit different. What?
The FKL usually has an issue with unitarity.
With unitarity.
Yeah.
Issue with unitarity is like really hard, and clever people try to handle this. There's Jan Balitsky, he's in JLab right now, and then he thinks that we have to take into account interaction of hard and soft degrees of freedom, which will restore unitarity. By itself, it's not unitary, but then it looks complicated, more complicated. There is a publication of Jan Balitsky on the attempts of restoration unitarity, but he thinks that infrared and the UV have to interact. So meaning that I can't find any corrections to my calculation, so I have to remember about infrared.
So
He's your colleague, right, Jan Balitsky?
yes. Yeah. You mean that this delta that you get is the same as in BFKL? It's,
Uh,
we have one
so
corrections.
delta,
Right.
well, first, let me define what delta. So, gluon structure function. Okay, it's like x g is 1 by delta. So we 1 by x is the power delta. So delta, so far we know Pomeron. And if you come on Friday, 11 and somewhere with me for another hour, we calculate correction to the 2 gluon exchange, 3 gluon, 4 gluon, 5 gluon, 6 gluon. And then I don't want to study it anymore. I want the whole thing. The whole thing I have to study quantum information. Quantum information spread along the chain of gluons, and this will come out to be 1/3. It was icing on the cake, so you forced me to give up my icing on the cake.
I still need to see it.